Okay, welcome to the panel session, Can Supercomputing Be Sustainable? Torbjörn Minde is my name. I'm the head of data center research at RISE, Research Institutes of Sweden. And I have a fantastic panel here with me. I will introduce them in a second. I guess there are people here in the audience that are experts in sustainability. So, and there is also probably some that are would like to get an introduction into sustainability challenges. So I hope there is something for all of us. And in this advent of large clusters, compute clusters, the question is, of course, okay, are we getting more valuable compute out of the resources that we use, or are this resource use, energy and materials going through the roof? That is, it's a lot of discussions on that going on right now. I hope we can address some of these questions here and discuss that. We will have a presentation from our panelists, and here they are. From the left, we have Dieter Kranzmüller from Leibniz Supercomputing Center. We have Satoshi Matsuoka from Riken. We have John Summers, also from RISE, our scientific lead, and Bronis de Supinski from Livermore Computing at Lawrence Livermore National Laboratory in the US. So they are on that order there, and we will have them to present. But I will start with some introduction. And then, so we will have a half an hour of introduction statements from all of us. And then we will have a half an hour of panel discussion and question and answers. And I hope you will enjoy today's session. So I will start then with a few slides here, introduction. So of course, when we talk about computing, the one thing that is a little bit, sometimes when you meet other industries or other fields, then I get a little bit annoyed of the fact that most goes to heat in our industry. If that would be the light bulb, it would be banned. So we need really to, the little use of the energy we have, we really need to get the valuable output. So this is a first thing, that the electricity going into a big cluster, most of it will go to heat. Okay, I was not showing that slide. Sorry about that. I didn't see how it works, this slideshow. Okay, we are at that slide. So most goes to heat. And where does the electricity go? There has been a lot of focus on the facility side of things for some time, to get down to, and the measurement tools that have been used, for example, the power user effectiveness, is focused on that facility side. And now with all the efficient facilities, this is how kind of maybe it's even lower part in some of the supercomputers, the facility side of things. Most goes to the IT. And in Europe, we are in Europe today, so in Europe, if you look at the energy use, don't have the supercomputers here specifically. It's all the data centers in Europe. We can see that some countries, of course, have a lot of energy use, but the percentage of the total energy use is different in the different countries. Some have more energy use for data centers compared to other industries. And these numbers, of course, have triggered the European politicians and the discussions on the value of all this compute has been a high topic. So that has resulted in a work that is called EU Energy Efficiency Directive. It started a long time back ago, but has the last years have a stepwise improvement of a kind of a new directive that will be laws in the different countries. And we now have a first version of this energy efficiency directive that the Commission adopted in March this year. And it defines a number of things, and one thing is the efficiency indicators that all the different facilities and supercomputers need to report and measure. And the size limit is right now set to 500 kilowatt of a compute facility. So above that, you need to report. But it might be different in different countries, depending on the law setting in different countries. But the question is, of course, is this enough? Is this enough for climate neutrality? Or is this an irrelevant discussion because we are getting so much value out of our supercomputers? The value for the society might be so high, so maybe this is an irrelevant question. But still, are we using renewable sources for the energy? What are we doing with the materials, the parts in our servers? What are we reusing them? What's going on with all the resources? So let's now move over to our first speaker, and it's going to be Dieter. Welcome here.
Thank you.
I will be in the back here somewhere.
Good morning. So I feel a bit strange being here talking about sustainability of supercomputers, since we're doing this since 2010 already. So this is more a look into the past of what we have been doing. And we have been doing this at the Leibniz Supercomputing Center, which is named after Gottfried Wilhelm Leibniz. Has nothing to do with the city of Leipzig or the city of Leibniz in Austria. We are in the north of Munich, and in 2010 we started to get our electricity 100% renewable. So there's only renewable energy in the center since more than 10 years. We also started to doing other things like running our systems with hot water cooling. So the first leadership class system came in 2012. And all of that is done in the block on the left side, our twin cube. You see on the roof of the top of the block, there is these white boxes. Each of these white boxes is cooling 2.2 megawatts, so in total we come up to 10 megawatts, and the electricity bill is an issue. So when we started doing that, the idea was not to say we want to be environmental friendly. We're happy we are environmental friendly, but we had to deal with the costs for the electricity, and that is a problem in Germany. What we are doing is we're providing IT services for scientists in Munich, in Bavaria, in Germany, and in Europe. And some of these systems are like these two here. This is the SuperMUC family of the system, the current two. On the left is SuperMUC NG, and on the right is SuperMUC NG Phase 2, which is kind of the AI extension. And both of these systems kind of have been developed in mind with being energy efficient. And the reason for being energy efficient is, again, not because we thought we need to do something for the climate. That's a nice side effect. But we are energy efficient on these systems because we want to make this system more powerful. So the more we save with the energy bill, the more we can put into the hardware, into the capabilities of the system. So making our systems bigger means making them more energy efficient. And as I mentioned, the system is hot water cooled, so at the moment we can go with inlet temperatures up to 45 degrees Celsius. And that means we're coming into the system with 45 degrees Celsius hot water. That takes away the heat, comes out with some more heat on the other side. And then again, the question is how much energy do we need to get back to 45 degrees Celsius? And the answer is none. Because if you look outside, temperature is sufficient to get us again below 45 degrees Celsius. And the question is then only, can we do something with the waste heat, and how much does it need to transport the hot water to the to the free cooling? We also took a look into the latest version. Is everybody's talking about AI, and this is a cluster for the Munich Center for Machine Learning. And that's what you go when you go to the providers and you ask them for some DGX boxes. So here we see 2 DGX boxes. And one of the things here is these are very powerful for what we do in AI. The problem here is, as Thor just mentioned, the PUE. The PUE of this air-cooled boxes is somewhere between 1.65 and 1.8. And that means that you are additionally to computing adding 65% to 80% in terms of electricity you need for cooling. So we said, could we take the same approach as in HPC? And that's what we see on the right-hand side. This is more or less our system. And what we have here is GPU nodes, in high density. We can put 144 GPU nodes in one rack, so to say, and that has a PUE of 1.03 to 1.05. So we're saving 50% of the energy for the cooling. And that's what I want to get to. I mean, the computational capabilities of these boxes is, well, comparable, with the difference that the right box is much more dense, and I can put 1,000 GPUs in 7 racks, so to say. So we're really kind of using the hot water cooling by going to the chips and everything, and you see this on our GCS booth. And the real message I wanted to give here is it's not just about what we can do in energy efficiency with the system. It's really the overall thing. So I think we should go away from just measuring the energy efficiency from the supercomputer, but more or less thinking about where does the energy get into the building, and what do we get out of the building, and how much energy do we consume overall. Also with the waste heat, what are we doing with the waste heat? I think just with the waste heat that we are producing, we can heat 40,000 households in Germany. Yeah? And that was something that needs to be addressed here. So I think we need to think about a holistic optimization strategy, think how we can get all these points together, and then kind of make really an impact, not only with the machines, but also with everything else around. And I think I had 7 minutes, and that's my part. Thank you.
Very good. So we are ahead of schedule. So let's, Satoshi, welcome.
Okay, hi, I'm Satoshi Matsuoka. I'm from Director of Recon RCCS. So, we have this big supercomputer Fugaku, which is actually very power efficient, although it's been developed in, around 2019. You can look at the current power status of Fugaku in real time right now. If you Google Fugaku status, and you can see that although the machine uses like 16 megawatts or so, there are 160,000 nodes, so it's only 100 watts per node, which is a pretty amazing number of power efficiency. Okay? But those are, and I completely resonate with what Dieter had presented, for example, with regards to more the holistic view with regards to thinking about power efficiency. Okay, but I'd like to think more holistic. So there are like papers out there, several of them. If you look on the archive or the various researchers, there are lots of papers saying, well, now AI is mainstream, HPC is mainstream, AI is mainstream, the AI power requirements in supercomputing data centers are not socially sustainable. Right? There are many papers like this. These are just the samples, so you can read them. Well, firstly, if you think about it, is this an issue in the first place? And this is a thing I got from the internet. I forgot to put the citation, I should. But training, let's say, like a GPT-3, which is a pretty large model, like almost 75 billion. And old hardware took about 300 megawatt hour. But Bitcoin, basically, soaks up 121 terawatts hour per year of global infrastructure. So, even if you look at these numbers, the power used by AI, I'm going to focus very much on AI because that's the mainstream HPC now, is peanuts, okay, compared to what's being used in other wasteful infrastructure like Bitcoin. But you may argue, okay, that the models are getting bigger, and if you believe in the chinchilla law, then of course the data needs to get bigger. So it's a quadratic effect. So eventually we'll have like GPT-4, now they can work in GPT-5 and all that. We'll be reaching the training compute flops required. This is not flop per second, this is number of physical flops required. We'll be reaching somewhere in the 1 to the 25th flops. And if you look at the the United States presidential order, they'll start putting restrictions on any model that's trained beyond 10 to the 26th. Okay. So how do they compare? Because we're trying, at the end of the day, what the human beings have done is to discover alternate form of intelligence. I mean, people can argue, but I have true belief that human beings have accidentally discovered an alternative form of intelligence with transformer-based large language models. Okay, so how much does a human being, and a lot of people say humans are much more efficient, but okay, how much power does a human being require to sustain its biology? It's about 110 watts, and the majority of the power goes to the brain. But societal power requirements to keep us alive, the heating, the transportation, manufacturing, everything to keep us alive and sustain this modern being that we are, is estimated to be about nearly 100 times that for the United States. Now you can argue Europeans and Japanese are much more power efficient, but maybe not so much, maybe factor 2, something like that. Yeah? So if you are to use that energy to train a PhD, which probably would be like hopefully comparable to GPT-5 or something, then biologically we'll be using 10 to the 11 joules, but the societal power would be nearly 10 to the 13 joules, a factor of 100 difference. Okay, so how much does it take to train a GPT-4 class model? Okay, let's say we hit the upper limit, 10 to the 26th. Then using Blackwell 2000 GPU, which is claimed to be 20 exaflops, effective FP8, and let's say it's about 3 megawatts. It takes about 58 days to train. So energy requirement is about 1.5 to 10 to the 13th joule. Not so much different from a human. So you can argue that biologically, training a very large, ultra large language model could be worth about 100 researchers like us in this room. Well, it can be masters. PhD really doesn't matter. But compared to the real researcher, like me, who travel all around the world and do stuff, then in the case of societal energy comes into play, they're not very different. Now, there are estimated 10 to 50 million PhDs globally, which is about 1.1% of the population. Or in the advanced countries like the US, about 1.1%. So a much higher PhD in more advanced countries, but still. So it took about 1 exajoule in biological terms, 100 exajoules to train, which is much, much bigger than training in AI. Yeah. And you can argue about how about inference. Well, we can do similar analysis, but if you do a different analysis, looking at the market. And there are, again, various claims saying inference market being like 10 times more than order of magnitude bigger than training, like the Barclays result study. Or some results say training is still bigger. But irrespective, it's only like order of magnitude. So even with the market cap analysis, is minuscule compared to human existence, of billions of people and millions who are intelligent. So what do we need to do? Well, we pursue. This is what a slide I stole from Rick Stevens. Well, he kind of gave it to me. But all the what Weekend is trying to do, and also partnerships with Argonne and others, is to advance AI for science, which is what PhDs do. And they do science in a lot of cases, and there are a lot of activities, but ultimately, the objective is this: to create scientists that will replace humans. Can we replace the scientific activity? Scientific activities like PDCA cycle, right? You hypothesis generation. You plan for experiment or simulation to validate the hypotheses. Conduct the experiments or simulation. You analyze. You write the paper. Publish. Then you go back to square one. And you repeat that cycle. That's how scientists behave. Can we replace with all the tools available with AI and being trained with a single scientific foundational model? Can we replace the scientists? How much can we replace the scientists? If we have to get us all out of our jobs, if we replace the majority of the scientific activities, then we don't need all those PhDs. Right? So, is supercomputing sustainable, especially with AI? You bet. Because in reality, this is very provocative. Well, at the end of the day, what we're trying to do is to advance science. And by advancing science, the probability of scientific discovery that will innovate the society, the chance will increase, and that'll advance the society. At the end of the day, that's what we're looking for. And then energy required to train the AI, or apply the AI, or even conduct the simulations, minuscule compared to what the humans require, and thus sustainable. Thank you.
Okay, very good. Can I ask now John Summers? Welcome.
There's a few more slides there that Satoshi didn't actually use.
Well, Satoshi has to have his 100 slides.
Yeah, yes. How many more? There we go. Thanks. So yeah, I'm probably slightly different here because I'm not actually running a high-performance computing data center, but we look a lot at data centers from all aspects, from operation to performance to the sustainability. And of course, the question about sustainability of supercomputers is one of the things that we're talking about today. And I thought I'd start with the top 10 requirements for a sustainable computer here. And I don't know, maybe my esteemed colleagues here will disagree with some of this, but I can't cover all of these in the 7.5 minutes, but I put them in order. Compute per unit of resource. I mean, that's something we just already heard. You know, how much compute can we do with the resource we're using? Energy efficiency is linked to that in some way as well. How energy efficient are we? Resource efficiency. So we're using material resources, we're using water in some cases, and I'm talking about a lot of different types of data centers here as well. Renewable energy, access to renewable energy, the cooling and the climate control that we use, and also the way that we monitor and report, because there is a requirement now through the Energy Efficiency Directive recast to do some reporting. And then there's some other things like waste reduction, using circular economy principles, trying to apply life cycle assessment to the data center itself and all of its IT equipment. In fact, the environmental impact of the IT is actually much larger than the building itself. Green building standards are used, and also location and siting. And I probably will say later on, because of the carbon intensity of the electricity source, put your data center in the north of Sweden. Compute per unit resource. This is something that is really interesting because, you know, efficiency in terms of what the engineering definition is, what we want is actually the compute, and what we have to pay for is the electricity. And of course, it's not an easy ratio because you can't measure digital services or anything like that in the same units. So the Green Grid has looked at this, and they have 8 proxies that you could use to try and measure the efficiency. But there is an ISO, which I'm not so keen on it, but it's one that's been mentioned as one of the ISOs that will be looked at in the Energy Efficiency Directive. And that's called the IT Energy Efficiency for servers. And it basically is peak performance to power demand. It's very much like the Green 500 is, the amount of flops you can get for your watts that you're consuming. So going on to say energy efficiency, what has been mentioned is the power usage effectiveness. It's a very misused KPI. It's one of the most important KPIs in the industry, and government like to talk about it. There is a graph there from the Uptime Institute, and that is they've been tracking the average the average value of that KPI, and of course, supercomputers are doing much better than the average, of course, because they're a bit more advanced in some of the technologies they use than in standard data centers. But it is the total energy consumed by the data center in the entire year. So you have to factor in the fact that you have seasonal effects, and that's the real reason the real way of using the power usage effectiveness. And again, another metric that will be used, the EN 5604-3 here, which is the renewable energy factor, and that's basically how much energy is coming from renewable sources, and that's owned or controlled by the data center. So there's some very important caveats of all these variables that go into these KPIs that are being used, that will be used, I think, when they collect the data through the Energy Efficiency Directive. What's interesting is the IT industry consumes far more of the renewable sources of energy than any other industry on the planet. And why is that? I think that's probably because they're all out there purchasing power agreements. Some of them are virtual, some of them, on-site power generation, which is a renewable source. So it's a very contentious issue, actually, renewable energy factor, but it's something that we will try to measure. Resource efficiency, one of the things that we can do is look at water as a resource, and water usage effectiveness is one of the metrics that can be used. Again, it's a standard EN 5604-9. And basically, it's the amount of water you consume in cubic meters divided by the IT equipment energy consumption over 1 year in megawatt hours. But there are other resources that are consumed in data centers. There's obviously fuel for backup. There is material resource, and space efficiency as well is another important factor for some data centers. And the fifth one, the penultimate one here that I wanted to talk about, and it's been referenced before, is obviously there is a metric for the energy reuse factor, which is the EN 5600 again. And again, the Energy Efficiency Directive is looking at this one. So how much of your energy crosses your boundary, that's the important thing, not used internally, but crosses the boundary of the data center and is used by a neighbor or another consumer. And that has to be measured over a year. All of the data here is measured over the year. And there is a thing called cooling efficiency ratio, which I don't think will be looked at, but there is an EN 5600-4-7 for that as well, and everything. So going to monitoring and reporting, the Energy Efficiency Directive that Tor mentioned there, recast, was actually agreed on the 14th of March 2024, and it's on the first phase of establishment of a common union rating scheme for data centers. And I noticed in his slide, Tor had the EU consumption. Obviously, the UK is not part of that, but the UK will not divulge from this. I think they will follow this as well, as they've been instrumental in it as well. And there's the carbon usage effectiveness, which is another EN 5600 rating, which we're measuring the carbon intensity of the electricity you use. So thanks for listening, and hopefully that's a taster of things to come to talk about. Thank you.
All right, so I don't know how many of you have seen me on panels before. I promise I will do what I normally do, but except that there's this first piece that I want to cover, which is normally I don't do any slides, but there's a point I want to make, and then I'll return to critiquing what they said. So first of all, the point is sustainable supercomputing is not about computing. So, we've seen that an abundance of metrics, all right, and probably the one we're most familiar with is the one on the Green 500, which is gigaflops per watt of LinPack, all right? And we've done a great job of increasing that over time. It's kind of flattened out recently. I do see that this doesn't include the result from this week, because I had to have these slides in earlier. Great, it went up another 10% with another up to 72 gigaflops per watt. Sounds great, all right? I'm going to come back to this. All right, so first of all, at Livermore, you may have heard, we're in the process of siting El Capitan. In order to be ready to site El Capitan, we had to go through a project that we called the Exascale Computing Facility Modernization Project. And what I really want to point out to you is bring to your attention that we had to do this project to be prepared for El Capitan and the next several generations of large-scale computers that we plan to deploy. So first of all, we had to increase the cooling to 28,000 tons with an additional 18,000 tons in these 6 new cooling towers that you can see right up there. And probably more importantly, we had to increase the supply to our machine room floor from 45 megawatts to 85 megawatts. Now, I should make clear that our plan is to be able to have a system that we're siting at the same time that we have a system that we are running. So El Capitan will fit into the envelope from our RFP. It will be under 40 megawatts. It'll be about 30 megawatts, all right? But that is a lot of electricity, all right? And, you know, we can talk all we want about how efficiently we use that energy. That's a lot of energy, all right? Just to give you an idea of the scale here, here's a standard American fire extinguisher. Here are just the pumps that are used for the filter station to drive the water through our facility, all right? So that's how we cool things. We get good PUE values. We get high energy efficiency by using direct liquid cooling. All of this is goodness, but the reality is, as Tor indicated, we're going to be using a lot of water. It's, you know, we've got complex system, multiple cooling loops, so that, you know, we don't waste a lot of water. We don't have to replenish that frequently, but we're using a lot of water. All right. Now, so the other thing is we hear a lot of talking about energy efficiency, all right? And, you know, the reality for energy efficiency, for actual codes, is what does it mean for an application to be energy efficient? And from at least, you know, a standpoint of using its energy efficiently, it means that you're getting your work done as fast as you can for the amount of energy that you're using. So think of this as a Pareto curve. I can go relatively fast and use a lot of energy, or I can go relatively slowly and use not so much energy. Both of those are energy efficient solutions, all right? Well, so where are we going to end up generally, right? If you get your users to make their code energy efficient, where will they choose to be? I'll give you a clue. It's not up there. It's down there. All right, so what's the result of being energy efficient? Is it less energy use? No. All right, you can argue, well, okay, you got your work done faster, and so then you're done, right? So what happens there? Well, I'll tell you, you're going to turn off your computers? No. You're going to run more jobs. And when you aggregate over that, you're going to use more energy. So energy efficiency is absolutely the wrong metric. So, you know, here's some other questions we can think about here. But I'll just point out the last question, because you, Tor, in the questions, you know, your opening, you definitely hit the fact that, you know, is energy efficiency enough for climate neutrality? And basically the answer is no. And so that's the first point that I wanted to make, is that energy efficiency is desirable. We shouldn't waste energy, right? Like, using energy to not get our work done, that seems kind of silly. But that doesn't lead to sustainability. All right. So then, just to kind of get the fun started here, let me return to what my esteemed colleagues had to say. So Dieter, I found it really interesting. You started by saying that you're using 100% renewable energy. Good. That is sustainability. But then you proceeded to spend the rest of your time talking about energy efficiency, PUE, a whole bunch of things that have nothing to do with sustainability. What was the title of this? I don't know. You did return at the end, but you didn't really focus on it to what do you do with the waste heat? That's a good question. I have to admit, like, what do we do in California? Well, there's not a whole lot of opportunity in California for what we do with the waste heat, because, have you been to California? All right, well, anyway. And then Satoshi. So this was interesting. So Satoshi's talk reminds me, I was watching the news the other day, and they came on and they were talking about a certain processor manufacturer that likes to promote their processors as being sustainable and energy efficient. And they happen to be making 1,000-watt processors. Let me tell you, a 1,000-watt processor is not green, okay?
It's colored green.
Well, you could, if you want to talk about branding, but I didn't mention any names. All right. But what I call that is it's the favorite game of politicians. It's called deflection, right? You ask me a question, and I answer a completely different question, and I pretend that it gave you the answer you wanted to hear for your question. And I think that's kind of what Satoshi was engaging in there, because he told us that basically AI models, hey, they waste less energy than humans. Okay. I don't know what to make of that. And then, John, I mean, it's interesting because you kind of proved what one of my points is, which is that, one, we don't really have the right metric for understanding energy efficiency, and even worse, for understanding sustainability of our computing use. All right? But you also reminded me of something somebody told me once, which is, like, when you go to, tell people why you're doing something, never give them more than 3 reasons, because if you have more than 3 reasons, you don't have any reasons. And so John said, here are my 10 metrics for observing energy efficiency. And I would say if you have more than 3 metrics, you don't have any metrics. All right? Anyway, so in the end, right, my point is that when we talk about sustainability of supercomputing, we're actually asking the wrong question, all right? Instead, we should be thinking about how can we use the computers to make a more sustainable world? How can we use them to address things like climate change? How can we use them to make it so that the society is actually headed in the right direction? Because supercomputers, look, a 30-megawatt supercomputer, I'm not going to tell you that that's a sustainable resource, but it could do a lot to addressing the societal problems that we're wanting to get addressed. And that's kind of my message.
Thank you, Bronis, for starting up the discussion, because I can see on the gentlemen over there that they would like to reply. So I think we would start with that. That would be fun. If we start with Dieter, could you reply a little bit to Bronis on his comment on your presentation?
No, absolutely. I would suggest Bronis should talk to the German Liberal Party. That's exactly the approach. Do more of the technology and it will solve everything. I'm not sure. I mean, I agree with Bronis. The things that we're doing in HPC are important, and energy efficiency is a side effect of what we do or what we contribute to society. And if we compare what we are doing on these systems to what other peoples are doing on Instagram or Snapchat or whatever the latest thing is. Bitcoin, yeah, Bitcoin was a good example. It's still, we are such a small area, yeah? So I'm not sure how to reply negatively. I just think if we take the full picture, then our systems is neglectable in terms, because we're doing something useful, no?
Okay, Satoshi?
Well, first,
your reply?
So I think Bronis agrees with me, because he says, well, computing for sustainability, which we are actually doing quite a bit on like machines like Fugaku. A lot of our workloads are sustainability workloads like disaster prevention, climate mitigation, all that. So we're doing a whole bunch of stuff. In fact, he's in agreement, because one of the most pollutant entities are humans. So if you replace humans with AI, then of course we can be much more sustainable, right? Now, but seriously, firstly, the important fact is this high-performance computing will permeate through the society in the form of, not just in the form of simulation, but all the derivatives of HPC, which are likely to be like AI-driven. So for HPC to lead the forefront, now it used to be a niche, now we're like the mainstream. AI used to be a niche, now it's the mainstream. So any of the energy savings or energy efficiency metrics we achieve in this community will likely permeate to overall lower the energy cost. So although we may be training AI very small, or doing simulation very small, but if there are 100,000, every hyperscaler uses 1 million GPUs to do something, then of course they need to be power efficient. However, still compared to what the society uses energy for, I mean, we're still small. And so we're using supercomputing or the AI technologies thereof to improve the sustainability itself. I think it's like same with transportation. We use energy to transport ourselves for good. We still use this energy, but that's for the good. But how do we measure this? So that's something we are starting to do, to assess the. So one of the goals I submitted to my headquarters is, as a KPI research institution, what's the valid KPI? And so we still haven't figured out the way to define it, but it's really the output of the societal benefits that we bring to the table for the amount of resources we use. So we can use all the resources, money, energy, so forth. But then what's the output? What's the economic impact of the society in terms of the monetary improvements, but also societal improvements and so forth. In fact, we have done a little bit of that with Fugaku, at least in terms of money. We work with consulting companies like Apparent Research to do a very candid analysis of how much of the economic impact Fugaku has had versus investment. And it turned out to be like almost 2 orders of magnitude compared to investment. And I think we can do very similar studies with respect to how much of the resources were put in to HPC versus how much impact it has had for the society in terms of the sustainability. Yeah.
Okay, good reply. John, usually you're the one that usually takes Brony's position. If I have an opinion, if you don't like it, I have another one. So what is your reply to Brony's?
Well, I think first of all, three metrics would have been useful. Yeah, I agree with you. There's 10 is a lot of things to consider when you. But sustainability is a really complex issue. I mean, and I've reviewed papers where academics have tried to put these metrics together to create one metric. There is no one metric that can measure this, because there are so many different facets to it. And the reason that I went through those, I mean, there are 8 metrics in the ISO standard. So at least there are 8, not 3. But the problem is that everybody. I mean, when governments start mandating on one metric, PUE, which is what has happened in some geographical locations for data centers per se, then it becomes a very divisive KPI, and people are and it's being gamed, and I think from it's not a sustainability metric. In fact, none of those metrics really tell the whole story of sustainability.
Yeah, well, I said I focused on kind of the energy efficiency metrics, but PUE is probably one of the worst possible metrics because it doesn't measure how much work you actually got done. So.
Yeah. No, but I agree with you entirely. And it's a really hard question because of the societal value of high-performance computing.
So we are now starting to move into that question. Is there possibility to, Dieter mentioned that, Satoshi now, John, science per kilowatt hour or something, or value? What can we do? Is there possibilities? Is there any possibilities to find a good?
I don't know how you measure it. I mean, one of the arguments that we're having for digitalization now is we talk about the scopes of emission. Okay, a server has, 17 of the 25 critical raw materials on the planet in it, and we're disposing of those at a rate of knots. So we should be trying to recycle some of that, but not all of it's captured. But to get a metric like that is very difficult because we've been talking about, well, if I don't drive to the library, but I download the book from the internet, that's using digital services, then I am offsetting my carbon. So it's carbon offsetting in one sense, if you wanted to talk. And that's really complicated to measure. And I think the same instance is how do you measure the worth of some compute versus others, I mean, looking at cat videos on Instagram, it has mental health. It could help mental health issues. Yeah. It could also cause problems as well. Yeah,
absolutely.
As it does, probably. Yeah.
Yeah.
But so not easy to. I don't know the solution. I don't know the solution to that. I'm probably.
Maybe Bronis can get a short chance for replying to the gentleman's replies, if you want to.
Sure. I see we're going to have a question there, so I'll try and be really short. So Satoshi claimed that I agree with him, and actually, much as I hate to admit it, I found it a little bit difficult to pick apart your arguments because, we're violating the first rule of panels, which is largely we're all agreeing. The reality is, I think that what we're trying to say is, as researchers in supercomputing, when people ask you, is your supercomputing sustainable, tell them that they're asking the wrong question.
That's right, yeah.
And, and you can respond to them by, we are trying to make the computing that we're doing as energy efficient and as ecologically friendly as it can be, but if you look at what it takes to do large-scale computing, it's kind of, in a way, counter to that unless we look at what are the energy sources, what are we doing with the waste heat, what are we, more importantly, using those cycles to compute. Computing Bitcoin, that seems, right? Like, taking a lot more energy to compute Bitcoin, it's still kind of a little bit of deflection, but the real point is like, what a waste for society there, right? I mean, anyway.
Yes, we have a question from the audience. Please state your name and then the question.
Yeah. Thank you very much. My name is Andreas Kochzech from the German Environmental Agency. I really like the talk, and I really do understand the point you have. Kind of, you're doing computing, supercomputing to make the world better. Let me put it that way. However, I also understand your criticism about sustainability and how can we make supercomputing sustainable, and I like to shift the question a little bit. So we are talking about renewable energy, green energy. We have heard Munich uses 100% green energy. Point is, green energy is flexible, and this makes manageable power a resource. And I wonder, so at supercomputing centers, we are able to manage our power draw. We can draw less or more power. Why or what stops us from leveraging this value we have in supercomputing centers, or even computing centers about the world? What stops us from leveraging this power we have here and manageable energy consumption?
And anyone would like to talk about grid flexibility or?
Yeah. So
Yes, Satoshi.
Yeah. So yeah, we think a lot about this, and of course, we completely, or the various analysis. We do tons of analysis with respect to how to make our infrastructure very green and all that, and sustainable. I mean, the amount of effort goes in is quite phenomenal, and then as are like cloud vendors. Now, there's an argument that the natural, these renewable energies, they're fundamentally, usually they're fundamentally less stable, like solar, wind, because they're affected by these natural phenomena. The only stable energy probably like nuclear, right? So, which is kind of sort of renewable, but there are different arguments against it. Okay, so let's say you can claim that the variable power, you can actually adjust the ratio of processing. So you have more power, you can turn on more nodes, and you can get more, you can get more cycles. And then, if you don't have power, of course, you turn things down. But if a job is like batch jobs, and you're not, you just want to sustain the average throughput, maybe that's fine. But then what you're doing, and this is an old argument, is you're not exploiting 100% of your capacity, which is a lost opportunity, and we don't want to slow people down, just like Brian has said. We want, we want to run the machine always at mostly at full capacity to get the sciences done, so that can affect the society. And also from a hardware point of view, if you, it's a lost opportunity because it's the same argument as is in the electric cars. Do you renew your car to a new one than electrical cars, which may be more efficient? But if you keep your old car, then you have to scrap it, and that may be more from a capex point of view. It's more energy efficient. It's the same argument. So these things take much more thoughts as to how to maximize both the opportunity and the capex, to exploit the capex costs as much as possible, while being as energy efficient as possible, and cope with the tremendous variance in terms of the output of these renewable power sources. And so it's not simple. There are some solutions, but those are things that we're working on.
Pieter has one to reply.
I want to make clear this story about the variability of renewables. We don't see that. We're doing this for more than 10 years now, and we saw that the variability is much less than the change in electricity consumption if you start a chop on our systems. I mean, that's where we have the big jumps, and that's once you're able to handle these big jumps. It doesn't matter if there's variability from the network, which might change if everybody is using renewables, but for the last 10 years, it was not an issue.
Thank you very much.
So I want to say one more thing to that, which is, I mean, the point is one that is reasonable upon first thought, but the thing that I think we forget is that the lesson from the broader society is that society has an insatiable desire for computing, and supercomputing is easily not alone in that. So the idea that we're going to allow, as Satoshi was saying, resources to sit idle, it's just not realistic.
Yeah. Well, just to give you a concrete number, for example, Fugaku, the material bill for Fugaku is about, well, it changes with fluctuation of currency, but about $600 million. Okay. And the annual electricity bill, we're like 90%, 95% full, is about $20 million. And and electricity cost is a little higher in Japan compared to US, but still that's at $20 million. So that's about 30 years worth of operation. Right? So the capex is, 20 years worth. So we can't really turn down unless situations where, like, we go broke, we can't turn off our power.
But what about the longer use of the equipment?
Oh yeah, yeah.
If you look at material use.
Yeah, we plan on extending the lifetime of our machines so that we use. We're planning to have longer lifetime of the machines. The difficulty there is a lot of these IT companies try to deprecate these resources on purpose. So if you look at like the end of life for these supports, they would take like 5-6 years, and these machines are still good to go after 5 years. And but we have no choice sometimes because they're ending their support, and we have to stop these practices. Tell the vendors to have prepare for much longer lifespan.
Yeah, that's an important point.
Dieter, yes.
Yeah. I agree. This is one of the problems. You have to shut down this machine because you don't get support anymore.
Yeah.
But I mean, there's an uptime report that's looking at the longevity of IT equipment, and it ranges from 18 months to 7 or 8 years. So there's a whole wide range of different activities out there, and there are reasons why some IT is being renewed at 18 months, perhaps. And we need to understand that, I think.
What about your curve, Bronis? Could we use the old equipment up in the upper left corner and the new equipment down there, right?
I mean, Satoshi's right that normally we plan on a 5-year lifetime for our systems because after 5 years it becomes cost prohibitive to do hardware maintenance. But we run systems actually frequently, typically more like in practice it's more like 7 or 8 years, and we've run several systems for 10 years. But you reach a point where although, technology advancements in terms of energy use and energy efficiency of the equipment improves, so then that curve is kind of assuming, given the system, how much energy do I use? Well, but if I vary the system, then I may end up using more energy, even though I'm using because I'm using older equipment that is less efficient. So I'm now on kind of one of the dominated solutions.
But if we exchange the energy efficiency to resource efficiency and include the materials used, what happens then with that curve?
Yeah, so
I'm thinking about the life cycle analysis of the whole server.
I haven't tried to do an analysis of that. We do a lot of analysis, and the reason at 10 years we tend to actually, by about 10 years, that tends to be the limit of how long we can keep systems in use, is there are several issues involved, but all of them end up becoming economic issues. It becomes more expensive to keep the system up and running because over time we have fewer and fewer of them running, so now it becomes more and more like, who knows how to maintain that system, right?
Yeah.
We have fewer people.
Yes, Satoshi.
If I can get very technical, and why, for example, we plan on right now making plans to extend the life of Fugaku to be like 10 years. Even when we deploy our next machine, we plan on keeping it for like 2 or 3 years for overlap, and also to because we think it's worth it. The reason is, the rationale is as follows. So most of the HPC jobs are, as we know, very much data movement bound, memory bound, especially. And if you're in this device physics or microelectronics and so forth, long story short, basically, the data movement energy is not decreasing rapidly, very, very slow. So if you have a machine now, if you have a machine 5 years later, 10 years later, 8 years later, the data movement energy reduction is minuscule. And you can find this out. You can do various surveys. We're doing lots of surveys of how, if we have a next generation machine, how power efficient it will be and so forth. The biggest impediment we have is that the memory, for example, the memory power is not going down, or the transfer of data from memory to CPU is not going down. Okay? So So power efficiency for real applications, not not green 500. Green 500 is not a good metric because it's compute bound. And if it's compute down, yes, the energy may go down. But if most of the HPC workloads are data bound or memory bound. So over generations, we don't expect to see much power improvement, power efficient improvement. And thus, keeping the machine now, like Furaku now, it will be, and even in 10 years, will be a reasonably power efficient machine. So, and then, based on this argument of the material will prolong life of the machine, will of course, if you don't scrap it, you're going to save a lot of energy. And of course, it's you extend your opportunity cost, recover your opportunity cost, is valid. So we expect to see over time, unless there's some innovation in memory technology, that prolonging the lifetime machine is the best way to be sustainable.
Mm. Yes, there are more questions on the floor. Yes, please.
Yes, I have a question and maybe a comment. I'm Łukasz Mirosław. I represent one of the hypervisors. The first comment is that science was always driven by curiosity. And we see that we see some examples of universities, especially in Switzerland. One of them is introducing a calculator to calculate how much CO2 and energy is driven by a single HPC job. So before you submit a job, you can calculate it, how much CO2 emission you generate. So I wonder if in future, are we going in the direction of that every scientist will get a CO2 quota? And then in the minds of scientists, it will be a question, do I want to, let's say, find out something interesting, something because of the curiosity, or do I want to, or am I negatively impacting the planet? Let's say that, put it this way. So I'm just thinking if we are not moving towards reducing curiosity in the scientific field, because you will have that.
But if you get the CO2 because of your output is really good for the CO2, maybe you can exchange.
Yes, but how to quantify it? That's exactly, and that's a good point about offset, carbon offset. So today, some companies, what they do, they still keep running their HPC systems with a traditional energy supply, but then they invest maybe in a startup that takes the CO2 in some of the blocks and then, let's say, bury it under the ground, and then they show how green we are, right? So the carbon offset is another way to trick the metrics and to show that we are more greener, that we are in the future. So thanks for that comment. And the last point I want to make, are we also calculating the energy efficiency of the systems that are negatively impacting the society? You mentioned social media. I'm pretty sure that there are also very big data centers. And is there any way to, or any statistic how much energy they are producing? And are we comparing ourselves as a HPC community with that negatively impacting community of social media, the streaming services, and I'm not talking about pornography, but this is also emitting a lot of energy. Are we also taking that into account when we are trying to compare ourselves? Yeah, thank you.
Okay. Yeah. So replies on that CO2.
Yeah, can I say something?
And the use. Yes.
Sure. I mean, I think one of the things from scheduling jobs based on energy consumption is an interesting one, and I think some people have looked at that. But obviously, if you know the energy that the execution of your job has taken, you know the carbon intensity of the electricity you're using, you can get the carbon impact of the work you've just done. And maybe we should be reporting that in our publications. You know, this particular simulation took some. Yeah. And of course, it pushes then putting data centers elsewhere. You know, why don't you put data centers where there's a low carbon intensity grid? You know, particularly for non-transactional work like HPC. Transactional stuff is, you know, when people want instant response, that's a very different kettle of fish. But you're right. I mean, it's if you look at climate change per se, if you consider data centers, there may be 3% of electricity consumption in total. I don't know what HPC is at. It's probably a very small fraction of that 3%. and electricity is about 15% of primary energy, you start talking about really small numbers. So what are we talking about? We've got bigger problems to solve, not worry about our HPC systems not being sustainable. And I think the question, it's the wrong question. And I agree with Bronis on that one. Yes, we should be asking, the question in a different way.
Dieter, do you want to respond to this?
Well, I was just wondering, I mean, the 3% is something that we are observing today, but if you take the prediction, what AI will be producing, the predictions, I think that was in Nature or something, was 12%, yeah? And 12% is an impact. Yeah?
But there's a hype curve.
Yeah. Of course.
You've got to wait for the hype curve
that
to
analysis,
pass.
but still. Yeah.
Read those
in the end,
yes, Bronis.
I mean, exactly, the point is that you have to ask, what should our society value, and is what we're expending, are the resources on the right things for us to value? That's the right question to ask. And, if you tell somebody, well, you can't run your supercomputing job that's going to, I don't know, on this topic, make it so that we find a perpetual motion machine, right? So, boom, energy problem solved, sustainable energy for the rest of our eternity. But you can't run it because it's going to take up too much, carbon to get there in the first place. You're making the wrong judgment, right?
Yeah. So by the way, on Fugaku, when you run the job, you get energy report. Okay? So we use that to incentivize people to be more power conscious. It's the same with cars. Like if you drive a car, and then why do you buy more fuel efficient cars? Or if you have the same car, you try not to step on the gas pedal too much, because it's mostly monetary incentive. There are some greenness, consciousness kind of incentive, but usually people drive sensibly or buy more fuel efficient cars to save money. It's the same thing with researchers. So initially we thought we'd give, instead of giving node hours, we'll allocate people energy, just energy as allocation. That was the first thing we thought we could do because we already have these energy reports. And also on Fugaku, people can pick different types of power modes on the nodes manually. So we tell people in the first place to run your job on the power mode that's most efficient, but does not compromise your runtime. If you compromise your runtime, that's an opportunity cost that's lost, so you shouldn't do that. So you should, but if you can run the job with the same, with the same speed, with the same time solution, but pick a power mode that's lower power and that's lower energy, that's your best bet. But how to incentivize that, right? So energy was one thing, but that was a little bit too, I would say, advanced, and people are not quite used to that. So we did an alternative by saying, well, if you save energy from your standard metric, what the expectation is that you will be using, and then you get credits for that. It's like, collecting coupons, getting credits for saving energy. If you accumulate these credits, then you can use that credit to prioritize your job. So in the batch queue, so you get a faster time solution effectively. And this has worked wonderfully. Right? So people are now trying very hard to save. If you look at the Fugaku's jobs status, you can see a lot of jobs are being run on fairly power efficient modes because people are incentivized. Because just like buying fuel efficient cars, they're incentivized. Oh, this isn't money, but allocations like money. Right? So time solutions like money. They're incentivized.
Okay, thank you. We have touched mostly on hardware. What about the software we are using in the supercomputers?
That's a question.
Are they? Yes, I know the questions. Are there efficiency gains to get there to better software for the supercomputers? Is there any gain? Is there any place to reduce the inefficient software
Well, I wouldn't. I think the metrics we were looking at were, and certainly the Pareto curve that I'm putting up there, it's a system metric. It's not a hardware or a software metric. It's saying you're running this problem, this is the question you're trying to answer scientifically, or the problem you're trying to solve with your supercomputer. You've got a given piece of hardware. How efficiently do you use it for that? So it's already addressing how we use it efficiently from a software perspective.
Okay.
But it's making good use of the hardware. I mean, a lot of this hardware has a lot of features that are probably not always used by the users. That's why I think we're entering into a more heterogeneous, application-specific type of hardware environment now, because we can get better performance when it's application-specific.
We have more questions on the floor.
Yes,
please, next.
Thank you. My name is Marek Michalewicz. I'm from NSEC in Singapore, and I live in Poland, very near to Ukraine and the war. So, but that's introduction. A couple of comments. We were thinking about some sort of indicator of usefulness of supercomputing computations. A few years ago, Hyperion Research presented something, an indicator which shown that $1 investment brings around 600 plus dollars in return. And the metrics that was developed by Hyperion was very interesting, because it measured short, medium, and very long-term implications of basic research that was done on the system. So that was there was some thought put into that kind of metric. But let me go to another observation. First of all, thank you for the panel. I thoroughly enjoy your views. But to me, it looks like apparently there is disagreement. But to me, it's like a few men blind describing the elephant, because you all talk about the same thing. From the point of view of thermodynamic systems, the first thing is to define whether the system is closed or open, and what is the domain, how large is the phase space. So, for example, the Swedish speaker was talking about the smallest system contained within a data center, plus a little bit, and has those plethora of indicators. Karl-Heinz spoke about slightly larger system, which included a little bit more in terms of sustainability. Satoshi picked up intelligence as a sort of basic thing, and of course based his picture on human and artificial intelligence. Fair enough. And Bronis took a much larger view of open system, including long-term societal impact and importance. So basically, you all talked about the same thing at different time and spatial scales and different boundaries of thermodynamic systems. And here I pose a question following Bronis, which is very important to me, is can we build digital twin of a war machine? Can we use computing to work on scenarios, war games, so perfect that there won't be any war? They would be useless in terms of intelligence, code breaking, and any move, any attempt of starting war would be useless.
Okay, thank you. Timing-wise, we are very in the end of the session, but I would like the final word from each, a short one from each one before, because the time is out. They will kick us out of this room. So if you start with Dieter, what is your final thought?
I think we should do a best effort to save energy as much as possible and to make our systems more sustainable with the ideas. And I think we're still doing good on that front, but there's more to do.
Okay, Satoshi?
Well, what Eric just said is including the war thing, what we're now trying to do on one of our big projects is to assess the effect of various things we do, like societal policies, how would they impact the climate, for example? And what are the so climate tied to things like economic policies. In order to do this, we have to create this massive digital twins. I think a similar thing is being done in Europe. So by using this, the digital twin, including simulation, AI, all the compute power, modeling capabilities, create these digital twins, and doing all these what-if analysis as to what we, what policies would be best to propel a society forward for sustainability. Well, one could be like, eliminate the scientists, replace them with AI. What are the effectiveness? What are the quantitative effectiveness of each of the policy that will lead to the sustainability? I think will be one of the big jobs, one of the major jobs of these types of large-scale compute facilities.
Thank you. John, final words?
I think, I mean, from supercomputing perspective, I think from the thermal management side of things, there's a lot to learn from the rest of the data center community, from the high-performance computing community, and because they've really pushed the envelope on that. And I think there's one thing that's been talked a lot about in standard data centers is stranded assets, which is a very big issue. You don't use your resource as well as you could do, and there's a lot to learn from HPC on that as well, because we use the systems, well, we should be using the systems effective to their full capacity. So there's a lot. I think there's a lot that supercomputers can give to the general computing community if they only listen, and if these guys only spoke more about it, how they do things.
Ronis, final word.
All right. Well, I'm kind of try and repeat the message I was giving earlier, because it's the message I wanted to impart, which is, to me, it's an ethical question. What kind of society do we want to be, and how can we use supercomputing to help us be there? I'm hoping the answer is that we all want to be a better society. Merrick's point, I don't know if that seems kind of like a pretty far out there vision. I don't know, maybe AI can help you get there, but let's try and be a better society. That's what I...
Yes, okay, thank you very much. Thanks for this session. It was very interesting. I have a lot of questions left here. We are not done. We have 1 hour, one more hour really, but the time is out. Thank you very much for being here with us, and thanks to the panel. Fantastic.